Okay, so this video is for the quiz number 3. So let's just do this one. Before you come to class, I want you to actually memorize all of these things right here. So kilo is 1000, deshi, so 1/10, and then centi is 1/100th, and then milli is like 1/1000th, 10 to the negative 3. The micro is 10 to the negative 6, and nano is 10 to the negative 9. Sometimes as the science advances, we tend to use pico more often. So these days we use picos. But as far as the general chemistry is concerned, I think nano is probably good enough. So what I want you to remember is that all of these things right here, and then all of these guys right here, you have to realize that these are just the numbers, okay? All of these things are just the numbers. So milliliter right here literally means it's 1/1000 liter right here, or the milligram is 1/1000 gram. So yeah, you just have to memorize all of these things. That doesn't really look good on this one, so I am going to use maybe a white. See, yeah, this one is better. All right, so you just need to memorize all of those guys, okay? It makes your life so much simpler if you actually remember all of these things. The kilo is the one that 1000, right? So let me just try to clarify my point here. 1 kilogram is 1000, okay? That's 1000. So 1 times 1000 gram. So kilo literally means this portion right here. So 1 kilogram divided by 1 kilometer, for example, right? All of these things, 1 times 1000 times gram, and then 1 times 1000 times meter, right? The 1000 can be cancelled, so which means that 1 gram is equal to over 1 meter. It's the same stuff. So you can literally directly cancel this kilo and kilo. That's something that you might want to remember, that one. That's key to actually make the key is to actually realize that, and then try to solve the problem as quick as you can, because you don't have that much time. All right, so given that, what is this milligram divided by milliliter is equal to, right? As I said before, the milli and the milli is going to cancel. By the way, the milli is 1/1000, right? But milli and the milli is going to cancel, so it's equal to gram per liter too. And the liter right here is a 10 centimeter times 10 centimeter times 10 centimeter. By the way, that's a volume, right? Liter is volume, right? Then 1 meter is 100 centimeter times 100 centimeter times 100 centimeter, right? So it's really 1000 liter is actually equal to 1 meter cube right here. So 1 liter right here is actually equal to 1/1000 meter cube. How did I actually get this one? Divide both sides by 1000, right? And then 1 gram is 1000 kilogram, right? Right, because kilo is just 1000, right? So 1000 kilogram. So that is going to cancel, right? So gram per liter is equal to milligram divided by milliliter is equal to kilogram meter cube. So all of these things are interchangeable, which means that, let me just try to open up the space here. If I have 50 gram per liter, I want to convert into the milligram per milliliter in some problem. Then 50 gram per liter literally means 50 milligram per milliliter. And some other problem, I may need a kilogram per meter cube, and that's also 50 gram per meter cube. All of these things represents exactly the same stuff. So that's what I wanted to actually tell you in the question number 2. Alright, then let's do the number 3 here. So 1 liter solution contains 100 gram sample. So 1 liter is what? 1000 milliliter, right? But you don't have 1000 milliliters, you have only 10 milliliters, right? So 1 liter is like this size, right? And then you only have 10 milliliters. This is equal to 1000 milliliter, right? Then 10 milliliter is like this big, right? And this contains 100 gram, right? Then how much is in here? That is a question, right? So to solve this problem, you are looking for the ratio here. The ratio is probably getting the ratio is the most important concept. I would say close to the most important concept in the chemistry. So let's just work on the ratio here. So it doesn't matter which one goes top or bottom, okay? The 1000 milliliters contains 100 gram right here, right? And then I'm gonna do the same stuff here, 10 milliliter, and this number right here has to be exactly the same. The stuff that I don't know is going to be right here. What is the ratio here? Now I'm gonna ignore gram per milliliter just because that they are going to show that they are going to be exactly the same anyway, right? So that's gonna be 1/10, right? What makes 1/10? If you put 1 here, that's gonna be 1/10, right? So that means that 1 gram in every 10 milliliter is same thing as 100 gram is in every 1000 milliliters. So that's what I want you to think about when you actually solve the problems. Visualizations is very important. Alright, so that was number 3. Alright, so let's do the number 4. How many nanomole? This N right here is actually a nano, okay? Nanomole. So how many nanomole? Many nanomole. If you have 200 milliliters, 5 nanomolar. So let's just go back to the definition of M right here, right? That's the concentration. And this is going to be the volume, right? So definition of mole molarity, this M, is number of mole divided by volume, right? Or the 1 liter. For this particular case, it's 1 liter, right? So, which means that I have 5 nanomole of stuff in 1 liter right here. Now we're gonna do the ratio, right? Again. So you have the volume, which is not quite 1 liters, it's 0.2 liter, right? Then I just convert the milliliters to the liters, right? Then I have 0.2 liter, and then I have how many nanomole? Now notice that I have exactly the same stuff from the left hand side and right hand side. Then this is going to be just a math problem, right? So right hand side becomes 5, and then what makes 5? If you actually have, if you multiply both sides by 0.2 right here. So I'm gonna put the x, right? So x is equal to, x divided by 0.2 is equal to 5, right? So what's x? X is equal to 5 times 0.2, which is equal to 1, right? So x is actually 1 right here. So every 200 milliliters, I have 1 nanomole. In every 200 milliliter. So that answers the question right here. Yeah. So the ratio is really the key here. Alright, so we're done with this problem. Alright, let's do this one. If the instrument can detect 10 millimolar, can I detect a sample of 20 millimolar? So if the instrument can detect 10 millimolar sample, then anything more than that concentration can be detected. So 11 millimolar you can actually detect, or the 15 millimolar you can actually detect. So does the 20 millimolar too. You can detect it, right? But if your concentration is less than 10 millimolar, for example, like 5 millimolar or the 1 millimolar or the 1 micromolar or the 1 nanomolar, all of those things are less than this detection limit. So you can detect those. So for this particular case, you have 20 millimolar solutions, so you can actually detect the sample molecule. Alright, number 5 is done. So let's do the number 6. Combustion of methanol. So we're going to have to write the balanced chemical formulas for this one. The combustion is very famous reactions, and it happens quite a bit in our life, so surrounding our life. So it's a good one to actually know how the combustion actually works. So combustion is that whatever the molecule is going to react with O2 to produce CO2 and water. Now, it's not balanced, right? So let's just do this balancing equations, right? So we're going to balance the number, we're going to start balancing the atoms that's the rarest, right? So the carbon looks like the rarest one, so let's just start working with the carbon first. So we're going to do the carbon. I have 1 on this side, I have 1 on that side, check. Next up is going to be H, right? Because H only happens only once on this side and then once on that side, right? So H, I have how many H's on this side? I have 4 on this side, right? 1, 2, 3, 4, right? And then I have 2 on this side. So I actually have to multiply this by 2. Now I have 4 on this side, right? So that's check. 4 and 4, right? Now oxygen, I have total of 3 on this side. I have 2 and 2, so I have 4, right? This side I have 3, so I have to do something about this one too. Now I already adjusted these things, right? Because it was balanced with the carbon. I have already put this one, so the only thing that I can adjust is right here, right? So that one right here, what's the number here? So that one right here, I need to probably add, this side is only 1, and then I have to have 3, right? Here. So what happens if I actually give them 3.5 multiplied by 2? Then 2 is going to cancel, I get 3, and then I have 4, right? 4 on this side, 4 on this side. So that portion right here is going to be 3.5. The reason why I have this 3 thing in here is because each oxygen molecule contains 2 oxygen atoms, right? So 2 and 2 is going to cancel, right? So that's that. So that is going to produce 3, that's going to produce 1. So required stuff is going to be 4. Okay, good. So everything is balanced according to me, but some of the chemists doesn't like to work with fractions, so I'm gonna multiply everything by 2. The reason why I'm gonna multiply everything by 2 is because this is the only fraction, and then if you wanna eliminate the fractions, you're gonna multiply everything by that number right here, right? So this becomes 3, this becomes 3, this becomes 2, and that becomes 2, and that becomes 4, right? I multiply everything by 2, right? So let me just clean up these things, just because I'm gonna use these things again. So 2, I have 2 here, and then I have 2 here, and then I have 4 here, right? Alright, so that's good. So now I have a balanced equation. Now all of these things, by the way, the ratio is in the unit of mole. That's really the key here for the chemist in general. So the ratio here, all of these numbers in terms of mole, here. So we're talking about mole ratios. So it's 2 to 3 to 2 to 4. That's the ratio here. So if you want to follow this reaction right here, you have to convert every number into the mole. So let's do the question here, number 7. So if the methanol have a density, how many mole of O2 is required to burn the 2 liter of methanol? I don't need a volume, I need a number of moles. To get the number of moles, you need to have a mass, right? So mass divided by the molecular weight is going to give you the number of mole, right? So let's do that one. So I have 792 kilogram per meter cube, right? Remember that one, that was same as the 792 gram per liter, right? Or that's just 792 milligram per milliliter, right? So any of these things are the same, right? So let's just use this one, just because that I have this 2 liter solution here, right? So how many gram of the methanol do I actually have? I have every 1 liter weighs 792 gram, right? And I have 2 liters of those. Then I just need to multiply, right? So 792 multiplied by 2 it's going to give you 1584 grams. So that's the mass of the gram of methanol. Right? Now, do I need a mass? No, not yet. Right? You're gonna need number of mole, right? Because that's basically what I need to actually use this chemical formulas. They're all in terms of number of moles. So you're gonna need to get the molecular weight of the methanol. Methanol is this formula right here. That's 15 gram per mole, 17 gram per mole. So that's going to be 32 gram per mole. Okay, so I have every 1 mole of methanol is going to weigh 32 gram. So how many mole is in here? So let's just calculate that one. So Excel. So 1584 divided by 32, right? So which is equal to 1584 divided by 32. That many moles of MEOH, right? Now, if I have 2 mole, so let me just try to clear up this portion right here. Oops, I need to erase these guys. Okay, so the ratio right here is 2 to 3, right? So I'm going to use that ratio right here. The ratio has to be 2 to 3. That's the number of mole, the number of NaCH3OH, and the number of oxygen, right? Now, why didn't I actually write the O2? Okay, right? So ratio has to be 3 to 2, and then I have how many more? I have 49.5. So I have 49.5 mole of CH3OH, and then I don't know this number right here, right? But ratio has to be the same. So how do I actually get this X right here? So I'm gonna do the algebra here. X is equal to 49.5 divided by 2 multiplied by 3. So I'm gonna do that one on the Excel. So this number is equal to this divided by 2 multiplied by 3. I get 74.25. 74.25 mole of O2. So that's the answer to question number 7. I hope this wasn't too difficult.